In today's video, we're going to take a look at reverse engineering a standard cell. And when I say reverse engineering, what I really mean is getting a better understanding for how this standard cell works. Now, if you don't know what a standard cell is, don't worry. A standard cell is part of the process design kit that we get from the foundry, the factory that makes the silicon chips that we're learning to make. And part of that big database of files is the standard cells. And the standard cells are like a big collection, about 150 tiny little cells, and each of them do a little thing like an inverter or an AND gate or a NAND gate or a MUX. And these are the basic little building blocks that we use to build up a more complicated digital design. I tried to keep the language simple in these videos, but if I forget and don't explain something, then you can always go to the zerotoasiccourse.com website and go to the terminology link, and I've got all the buzzwords there. So let's get started by looking at a simple example, in this case an inverter. So an inverter is a way of just inverting an input signal. So if we get a 0 in, we get a 1 out. If we put a 1 in, we get a 0 out. In Verilog, we'd write something like this to use it. Out equals not in, and this not is what is going to become the inverter. Now, how does the inverter work? We've got a circuit diagram here, and we've got two types of transistors, MOSFETs, and I'll be using those terms interchangeably. So we've got a P-type MOSFET here and an N-type MOSFET here. An N-type MOSFET switches on and allows current to flow when the input goes high. And the P channel is the opposite of that. So if the input is high, it's not conducting, but if the input goes low, it does conduct. And here we've got the layout in the standard cell. So this is the little building block we get from Skywater with a simplistic key here. So we've got the P FET here, that's the top there. And then we've got the N FET at the bottom there. We've got this kind of blue color, that's local interconnect. And this red is the gate, and that's made of polysilicon. And where it overlaps the diffusion layers, the N and P diffusion layers, that's how we get the transistors. We've got the ground connection at the bottom, the power connection at the top, the input A and the output Y. So let's take a look at how it works. When the input is low, 0, this top MOSFET is going to get turned on because it's a P MOSFET. So it's going to pull V out up to 1, and the bottom is going to be off, so it's not going to be doing anything. When the input is high, the bottom MOSFET turns on, connecting this to low, so the output becomes low, and the top transistor, the PMOS, is turned off. So they're either one on or the other on, but never both at the same time, and the output is always doing the opposite of what the input does. And over here we can see these two transistors. So here we've got the input, it connects to both of these transistors. We've got the N FET at the bottom, the P FET at the top. The outputs connect to each other, and then the outputs join together and become the Y. So this is a simple example, the inverter. And I've always kind of been able to see how this gets laid out because I'm used to the schematic symbol here. So I thought I'd take a look at a more complicated standard cell, in this case a 2 MUX. So what this means is basically like a switch. So depending on what S is doing, it's connecting A0 or A1 to the output. So if S is 0, then A0 gets through to the output, and we don't care what A1 is, that's why it's an X. Whereas if S is 1, then A0 is ignored and A1 makes it through to the output. And this is how we'd write it in Verilog. This is one way we can say assign the output is equal to, if S is 1, then A1, if S is 0, then A0. And you can get these standard cells by going to this link. I've basically copied the picture and put it in here. But we can see it's a lot more complicated. So given that what we've just looked at before in the previous slide, and you know the key, what I'd like you to do is to count how many transistors you think are in this standard cell. So just pause the video, count them, and then resume the video. So you probably got it right, 12, and that seems like quite a lot to do this job. And I was wondering, like, how do these all get fit together? And it took me longer than I expected to work it out backwards. So one thing I wanted to show in this video was my process in how I did that. So the first thing I did was the first thing I didn't do was label the transistors, and I kept trying to remember where things were, and I kept getting stuff wrong, page after page. So in the end, I just loaded this up in the GIMP editor program and labeled these so that I could, when I drew out the transistors on a piece of paper, I could number them all, and then I could make sure that I got my wires correct. So if we start off with the input, so this S, and we've got two places where it can connect. We've got this via dropping down to this red polysilicon gate, and we've got a P and an N MOSFET here. And then if we look on one side, we've got this positive connection, and on the other side, we've got this local interconnect that comes down here with another via. And then here on 2, we've got on the one side a ground connection. This is connecting to the ground, and then on the other side it also connects. So this is the same structure that we've just seen. It's just like an inverter. And I've put this here, 1 and 2, and over here we've got 1 and 2. So this is kind of, we've got S here, and then coming out the back, we've got not S. We've also got these other two, 9 and 10. So if you trace this local interconnect, let's see, it comes along here, goes along the top, comes down here, drops to another via, another polysilicon gate, we get 10 and 9, and they are both here. So I went through gradually and labeled everything up, connected to everything was, and then on this page, I kind of regrouped it by putting the things together. And what I discovered is basically 4 inverters. We've seen this pattern before. We get a P and an N, and at the top you've got positive, and at the bottom you've got negative. So we've got our input S going to not S, and then we've got our A0 and our A1 inputs, and they both are fed into what looks like an inverter that then go back, join into another inverter and become our output X. And the clever thing is that we've also got these other P and N channel gates on the top of both of those inverters, and those are then controlled by the S and not S signals. So if we've got S is 0, so the A0 should be functioning, S is 0, then this one, S being 0, turns on the P FET, and not S turns on, because not S is now 1, turns on the bottom. So it means that the top P channel of this inverter is connected to the positive, and the bottom N channel is connected straight through to ground. So this inverter is functioning. Whereas this one is the other way around. It's not S at the top and S at the bottom. So this remains unconnected. So whatever A1 does, the output never does anything, because neither of these FETs are connected to anything. And then the signal goes through here, is inverted, so then the output is the same as A0. So we get the truth table working out. And the opposite happens if S goes high, not S then goes low, and the opposite things happen. This inverter is disconnected, this inverter gets connected, and then basically A1 is connected to the output. So the latest book recommendation that I got is CMOS VLSI, designed by West and Harris. And just getting started with that, I noticed this great passage about combinatorial logic, and it really kind of explains how the standard cells work. You get some of the transistors that are doing the job, but you have these pull-up, pull-down networks that are engaged or disengaged, and that's why things tend to look like chained or paralleled inverters. So I hope this video is helpful. I hope it inspires you to choose your own standard cell. Go to the Skywater PDK website, pick a standard cell, try to reverse engineer it, extract that netlist, make sure that it matches up with the truth table, and get a little bit more into ASIC design. And if you want to learn how to go on and design your own chips and get them made, then you could check out the 0 to ASIC course.com website and look for the tickets for the course on the tickets page.